Hey folks, Emily here. Today you are going to learn how to train your own language models on AWS Trainium with Amazon SageMaker HyperPod and EKS. Let's dive in. All right, so again, this is a tutorial about multiple nodes. So we're in the space of distributed training. We've got EFA that's connecting us across the nodes, and we want to figure out how to do this in an optimal way. So what happens actually when we're trying to train language models in distributed cases is that we're adding more and more and more accelerators to the overall cluster size, the overall world size. When you're in a single node example, this is not necessarily a problem. Once you increase the overall cluster size, what happens is that the likelihood of a single accelerator going down increases dramatically. This is the case for every accelerator, right? In the words of Werner Vogels, everything fails all of the time. This is true with every accelerator. So hardware failure happens constantly. And in hosting, this is less of an issue. In single node training, this isn't an issue. But as you try to create an increasingly larger cluster to pre-train, fine-tune your own language models, what you need is a reliable way to mitigate and manage hardware failures. This is a critical necessity in order to train your own language models effectively. You want to keep your compute utilization high. You want to keep the performance of your overall compute cluster high. And it's challenging because you're doing all of this at the same time. So you have one model that's split over multiple accelerators, say with a TP degree of, say, 32 or 64, your tensor parallel degree, which is the number of accelerators that you need to contain your model, essentially to host your model. That's what we call the TP degree. Now, when you are working at very large cluster sizes, you will not have just one copy of your model. You will have many, many copies of your model because you want to step through your training data as quickly as you can, because you want to train your model as quickly as you can. So the number of model copies that you have is your data parallel degrees. So that's the number of complete model replicas essentially that you have. So you have many different model replicas. All of these model replicas that are themselves split across multiple accelerators and in many cases multiple instances, this entire world needs to be synchronized, right? Because you need to step through your training data, you need to compute the loss, you need to update the parameters of your model, you need to use the optimizer to descend down your learning rate, descend down your loss function using your learning rate, etc. There are so many cases where this can fail. And if even one piece goes down at any moment in time, normally your entire cluster halts, and it's going to sit there halted until someone goes and figures out if there was a data corruption piece, if there was a software corruption, if there was a hardware corruption, etc. And so all of this inefficiency leads to a slower time to train and ultimately higher costs. So to address these challenges, AWS has developed many capabilities to make this easier for customers, faster and more efficient. So Amazon SageMaker HyperPod is a managed distributed training cluster that you can use to ensure that your cluster is resilient, to ensure that the accelerators are healthy when you launch your nodes, to ensure that when one of the nodes goes down due to a corruption anywhere, in that giant stack that you're working with, any piece of those fail, HyperPod will help you recover from that. In the overall scope of your cluster, you can have multiple nodes that are available as backup and recovery to enable you to reduce the time to train by up to 40% through a faster recovery time and then lower overall costs. So essentially, here are some of the key features of SageMaker HyperPod. Fundamentally, HyperPod gives you a resilient distributed cluster environment with proactively screening the health of the inbound nodes, continuous hardware monitoring, and automated repair and job resumption, which enables your cluster to heal faster and more efficiently. Overall, this enables you to train at much larger scales and with a much better experience, keeping your overall job more efficient. This enables you to develop and test with a greater variety of jobs, of models, of methods, which enables you to scale better utilizing AWS topologies such as EFA and single spine node topologies. And so all of these are excellent ways that you can train your own extremely large language models on AWS today. Now, in order to provision SageMaker HyperPod and in order to launch jobs on SageMaker HyperPod, we're going to do that through the control plane of Amazon EKS. So Amazon EKS is a managed Kubernetes service that enables you to use common Kubernetes control flows like pods in order to provision resources and launch jobs on those resources. We have a fully built workshop that you can use to step through and understand how to use Amazon EKS and the kubectl to create and provision jobs, which are then launched on the SageMaker HyperPod clusters and content. And so this is the scope of the demo that you're going to learn about right now. And before we jump in, I want to help you understand how you can train your own models with SageMaker HyperPod and then with Trainium. So the workshop will show you step by step how to pull down a pre-built recipe for distributed training and for distributed training of Llama-based models, which you can then apply onto SageMaker HyperPod. But I want you to already start thinking about how to use that with your own artifacts. So a couple ways to do that. Step one is identify your base container. So most likely you're going to use a DLC or a deep learning container that has packages pre-built for you. What I like to do is pull down a pre-built container that again has a full build of the Neuron SDK. And then in Docker, you can extend that container with your own packages and content. So you're going to extend your container to use the backend of the DLCs and the package versions that already work really nicely, and you're going to extend that with the rest of your scripts and your content and the rest of what you want to accomplish in your application. And then as we learned in the previous video, NeuronX distributed training, NxDT, is a way for you to use our pre-built recipes for pre-training, for inference, supervised fine-tuning, and alignment in order to optimally train on Trainium. So you want to develop your training scripts using NxDT on top of a base container which you've extended with any additional packages you need. Once you have your container and you have your training scripts, then you need to go into the EKS workshop and the HyperPod workshop to modify the launch configs and modify the launch scripts. There are bash scripts, there are YAML files, there are commands that are managed for you and that are maintained in the context of the workshop. What you need to do is study those and modify them to use the parameters that will enable you to train your model optimally. So that's your third step, is modify the launch configs and the scripts. Your fourth step is to run the commands. So the commands to launch and provision the cluster. And again, you're going to use the kubectl to accomplish that through the EKS control plane. So you're going to launch the cluster with HyperPod. You're going to use the command to compile the model. So again, we have a bash script that shows you how to compile a model through NxDT. And then you have another command to train the model. So all of that is shown for you in the following workshop. And now we're going to go through a demo. So this is an incredibly comprehensive demo that's going to show you step by step the key components you need to accomplish for hosting and training at very large scales on SageMaker HyperPod. If you want to sit down with me for the next hour and take a look at what Jianying has built, this is the place for you. If you want to go do something else, that's fine, but we're going to check out this demo.
I will do a demo on how to distribute the training workloads on the Trainium 1 instances with SageMaker HyperPod. The first step, we want to deploy one editor stack. You can set everything up on your local cluster, but the SageMaker Studio code editor provides very convenient working environment. So as a first step, we can click this. There's already a template set up. In this template, it gives a stack name and also the EBC size GB. Because this is the editor, a small size is good enough. For the instance type, you can choose the smallest one, the MLT3 medium, and then you give the resource name prefix is the SageMaker HyperPod EKS by default. And after everything is set up, you can click agree the confirmation and create the stack. The creation can take about 10 minutes. We want to deploy the SageMaker HyperPod on EKS stack. We also have a template available. Click this button, you will see the template will show up. It gives the stack name. So all the VPC, everything has been default value, and also the VPC CIDR, all those are default. Just to make sure you set the right availability zone. Here we want to use US East 2 AZ3. We know there are instances available there. And then moving down, this is the HyperPod cluster name. Give the name you want it to be. And here, make sure you choose the right accelerator instance type. By default, it's a G5 instance, but here we want to use the Trainium 132X large. And you set the right accelerator instance account. We will use one instance in this demo. This is the host node. You can use the default one. And after everything being set up, we can choose just click here and create the stack. It will take about 15 minutes for the creation. Stack creation is complete. We can check the cluster information right now. Just search the SageMaker HyperPod AI. If you look at the HyperPod cluster management, you will see the cluster that is just created. If you click here, you can see more details here. So we can install the Amazon CloudWatch observability. So we can click the installation. It will install. And also, if we want to check the instance details, you will see we have the head node and the accelerator nodes. So we will verify the connection next. We can start verifying the cluster connection. Remember, we created the SageMaker Studio editor. We can work there. Studio. And set it up, choose the right setup, and now we can confirm the connection with the phone. We first use this command to source all the environment variables. You can see this environment variable has confirmed all the SageMaker cluster name as well as the instance ID. So by the way, so after the warning part, everything is not usable. Just make sure the above one, like the region, the cluster name, the VPC ID being consistent with what you created in the stack. Is to verify the Helm installation. With this, After verifying the Helm installation, we should be able to check the FSX file system setup. So to install the file system, to create that, we need to install the Lustre CSI driver first. Yeah, set up the driver with the cluster name, and then create the IAMO role on top of that. And after that, we can verify the service account with the IAM role. Verify this installation, and then the last step before we can create the FS Lustre is the deploy FSX Lustre with Helm. Okay, after this, we should be able to create this FSX specifically for the fine-tuning setup. With this, we wanted to create the manifest file, the PVC YAML file. Okay, this is the persistent volume claim is generated. We can check the file there. Okay, it is not found. It will take about 10 minutes to create this volume. Okay, as you can see, right now the FSX cluster status set as bound mode. So that means the creation is successful. We can also check the FSX in the console file. So if we search here, you can see this file system is created successfully. As a next step, we are going to mount this volume to the container, to the cluster. That again using the EKS to apply the manifest file. So this is a pod. We can see this is the pod status. The FSX claim right now is running state. So that means the file system is ready for use. Infrastructure, the SageMaker HyperPod cluster setup is successfully done. We should start build the Docker image and start the real training. The first step is to log into the ECR and pull the Hugging Face PyTorch training neural X image. So this pulling could take about 10 minutes because the Docker image is pretty big, about 20 gigabytes. We can check the source code of the real training code. We will download the source training code and build the Docker image, combining the base Docker image we just downloaded and the source code that we are going to train. So if we look at to the source code, we will use the Docker file showing this source code in the if we click the link. So basically, it will use the base Docker that we downloaded from Hugging Face, the PyTorch training neural S, and install all the dependencies. And we will copy what is available in this source code to this to the container and build a new customized container where we will launch the real run. So after downloading the source code, and we already saw the Docker container file, we will build the Docker image and push that to the ECR, like the Docker image. This build process will take about 10 minutes. The build complete. Right now we can push the code, the build container to the registry. This push process will take another 10 minutes. It was pushed to the private registry. So we can see Docker image. That is available right now. Okay, right now we can start the training process. In this repository, we can see we already have the templates file that is for the manifest file. We can use run this generate job spec to generate the real training file. So then we can do this bash. When we run this, we can see all the Llama files generated. It's generate the data processing file, generate the compile manifest file, and the training manifest file. And because after the training, we need to consolidate the checkpoint and then merge the LoRa adapter with the original checkpoint. So we still need the LoRa merge LoRa manifest file too. So the first step, let's do the token and data download and processing. Okay, right now, if we look at the pods, you can see right now the Docker container is being downloaded, so it will run on for the tokenizer. The container for the token processing, data processing is running. While it's running, we can use the kubectl logs to check the running process. You can check the log output. Now the pod actually complete. So you can see the status right now is completed. Next step, we should be able to compile the file right now. Compile the training graph. Again, we can just use the kubectl to apply the compile path to manifest file. And again, we can check the status of the file. Right now, it is running. We can check the logs output again using the kubectl logs. We can check this one. Yeah, here you go. It's compiling right now. It will take about 10 minutes-ish to have the compilation done. The compilation is done. We should be ready to launch the training script now. For the training script, it is called a launch path to train.yaml file. So we can do that. Apply this train script. The training started. As you can see, right now the job is running, the training job here. If we look at the training script, this one, we can see the hyperparameter there. This is the hyperparameter. We set the data precision as bfloat 16. Right now we use the only 8 workers. That means the neuron right now we only use the 4 chips, 8 cores. And the max sequence length we set is 1K, and we are using the data set that is publicly available. And the model path, right now you can see we set everything and the FSX directory. That is the file system we created. We set as TP8 and also the weight decay as 0.01. So as again, we can check the logs, like we did check others, like -f. That is the training worker JavaScript, -n kubeflow. We can see right now it's reading the cache file. The whole training process will take about 10-20 minutes-ish. You can see the training is ongoing. So if you look at the initial loss value, so 1.8. So right now, as the training ongoing, it keeps dropping. And also, we save the checkpoint every 400 steps. So right now, we already have 2 checkpoints saved. While the job is running, we actually can enter the pod and check what's going on there. So right now we are in the accelerator nodes right now. We can check like the neuron top to check the status of the hardware utilization and such. Since we are using the TP equal to 8, that means only 8 cores are being used. As you can see, there are 8 cores being active. Training is completed. So we can check what is the file is being saved. So we know the checkpoint is saved somewhere. As you can see, we have the active pod FSX app, because we know that the FSX file system is mounted on this pod. We can log into this pod using the kube exec, like we have checked the training pod. So as you can see in this script, in this file directory, we have the data, the path fine tuning, and we check the checkpoints here. You can see there's 3 checkpoints being saved at a different time step. The last one is the checkpoint 1200. As you can see, because this is running with 8 workers, so the checkpoint is distributed saving. After the training complete, we cannot use this distributed checkpoint. We need to consolidate them to be a single one. So right now we will consolidate the distributed checkpoint using another manifest file called consolidation YAML. So right now we can check what's this one is running as well. Okay, so the consolidation is running. After checkpoint consolidation, we can see right now what the checkpoint format is like. So if we look at the data directory, PFT model checkpoint, so you will see the final directory. In this final directory, you can see that that is the standard way of the checkpoint saving. There's a JSON file, tokenizer JSON, and also there's the training bin file. So if we look at the sharded, so this is the final checkpoint so after the consolidation, we should be able to merge this checkpoint with the trained checkpoint we can call it adapter checkpoint with the original checkpoints as the total LoRa fine-tuning result. So the training process is just apply another manifest file. This is after this you will see the final checkpoint. You should be able to deploy that to for your inference. So this is the whole process of the fine-tuning. Thank you very much for watching.
All right, Jianying, thank you so much for that amazing demo. I love learning about all of the commands. I love learning about how to set up my bash script. I love seeing that the job is actually running on HyperPod. I love monitoring it. I love watching the steps. It's so cool. And so with that, thank you very much for this video. Thanks for spending the time with us. A couple call to actions. Number one, again, many models are well supported today from documentation and samples. You can pull these down through NxDT, pull them down through Hugging Face Optimum Neuron. So again, giant shout out to the team. There are so many amazing engineers and developers who pull this together and make it possible to do large-scale distributed training and hosting on Trainium and EKS. And so just a giant thank you to the team. So with that, thank you very much. I'll see you next time.